SwayamPrabha. Digital India. Educated India.
Hello. So we shall continue our lecture series in astrochemistry. This is lecture 4. And by the end of last class, we had looked into the formation of neutrons, electrons, and proton, the 1h1 nucleus. All right. So this happened approximately after 10 to the power minus 2 seconds after the Big Bang, and the temperature had cooled from around 10 to the power 32 Kelvin at the start of the Big Bang to like approximately 10 to the power 11 Kelvin. Mind you, 10 to the power 11 Kelvin is still very hot. Okay. Despite 10 to the power 11 Kelvin being very hot, it has cooled down significantly, starting from the temperature of approximately 10 to the power 30 odd Kelvin at the initial point when T equals 0, as we understand based on the standard model of cosmology. Okay. So we shall now continue with understanding how the other isotopes of hydrogen, that is 2H1, which is also called as deuterium, and which is called as tritium. How were these two formed? Okay, we'll also look into the equations responsible for the formation of deuterium and tritium. So we know that once a proton is formed, the proton undergoes nuclear fusion with a neutron to give you a deuterium. And in this process, whenever neutrons are involved, most often you have gamma rays. Gamma rays, which are a part of the electromagnetic radiation. So the gamma rays are also released every time, most often when a neutron is involved in the nuclear synthesis. Okay, the nuclear synthesis of some of these elements. So now we have the formation of deuterium, which is another isotope of hydrogen, and likewise the formation of tritium happens when a deuterium fuses with another deuterium atom to give rise to the formation of a tritium isotope along with the hydrogen itself, the 1H1 or the proton nucleus itself. Okay, right? So this is how the isotopes of hydrogen are formed. In the last class, we looked into the formation of hydrogen itself. The other isotopes of hydrogen are formed from these, Big Bang nuclear reactions. And if you notice that, for example, if you look at the formation of tritium, it is not happening, directly from the reaction of hydrogen with, a hydrogen, 1H1. This is what we commonly call as hydrogen itself. The 1H1 is what is called as hydrogen itself. It does not happen with the reaction of 1H1 with 2H1. It happens with the reaction of when 2H1 fuse together, and we have the formation of tritium, and along with that, the proton nucleus is also actually given off. Okay, this is an important point, typically because the idea of energy dissipation is something very important. Okay, right? And when these things happen, now you never normally see like two entities, two reactants becoming only one reactant. There's a lot of basic physics involved here. Basic high school level physics. What is that? It is that when two reactants, that is like deuterium isotope, when they react with one another, if they had formed something like only one entity, the energy formed, the energy released with the formation has no way to dissipate, right? It is only with the formation of another molecule that the energy gets dissipated. And that is also why the energy can either be transferred to another molecule, or the energy can be absorbed into the medium in the form of electromagnetic radiation. So the concept of energy dissipation is something very important, and we shall not only see it in the nuclear reactions which lead to the formation of the fundamental elements, but also in a lot of astrochemical reactions themselves. Okay, so please keep this in mind for now. I'm not writing anything on the board because I just want to introduce this notion to you. And as we study more and more of astrochemical reactions, this concept of energy dissipations becomes very important. Okay, just note it down right now. Okay, let us now look into the formation of helium. Now on Earth, we are mostly familiar only with the 4He2 isotope. However, as it happens, along with the Big Bang theory, along with the Big Bang nuclear reaction, the 3He isotope is what is actually formed first. Okay, right? And how is it formed? You have the fusion of a deuterium along with a hydrogen to get the 3He2 isotope of helium. And notice that you've already had like charge 1 + 1 is 2 and 2 + 1 is 3, charge and mass balance. However, we call our concept of energy dissipation. Now whenever two reactants become one product, right, the excess energy that is released, that has to be given off to some other entity, correct? Right? So therefore, we also have the formation of gamma rays. I mean, the formation is not the right way to put it. We also have the liberation of gamma rays as part of this reaction to ensure that energy dissipation happens smoothly, and so that the excess energy released due to this reaction does not result in the reverse reaction actually happening. Okay, right? So that is how the 3He2 isotope is formed. And lastly, we shall look at how the 4He2 isotope is also formed. Now again, the 3H1, that is the tritium isotope of hydrogen, fuses with your deuterium to result in the formation of the helium, which is also the core of the alpha particle. The doubly ionized helium is what is called as the alpha particle. Okay, right? That is formed along with, now again see, so here, right, you have charge balance, but mass is not balanced. So this is accompanied, the formation of the 4He2 is accompanied by the liberation of also neutron. All right. So this is fundamentally how, right? This is fundamentally how hydrogen and helium, which are the first two elements in the periodic table, they were synthesized, right during the Big Bang. When I say right during the Big Bang, I'm not talking simultaneously. What I'm saying is that a few seconds after the Big Bang, we're talking about, all of this must have happened approximately, it is said that all of this has happened approximately 180 seconds after Big Bang. And hydrogen, helium, and some lithium was also synthesized from these nuclear reactions. All right, so imagine the hydrogen, the helium, and the small amounts of lithium, they were all formed, just 180 seconds after the Big Bang. And how old did I tell you was our universe in the last class? It's approximately how many years? 1.38 into 10 to the power 10 years, which is like 13.8 billion years, right? That's how much time has elapsed since the Big Bang has happened. Now, notice when the hydrogen and helium were formed. The hydrogen and helium were formed approximately, 3 minutes after the Big Bang. So you can imagine now that almost in the universe, right? Hydrogen and helium are the oldest elements in the universe. It's kind of a cool idea, right? That hydrogen and helium, especially hydrogen, which is part of almost every hydrocarbon. That hydrocarbon, lots of organic and inorganic molecules, all of them contain hydrogen. But what is the source of the hydrogen? It all goes back to the Big Bang, and these were formed within 3 minutes after the Big Bang. So the hydrogens are very old. The hydrogens present in the universe are very old. They're not just old, okay, they're also the most abundant. Can you guess, the percentage of hydrogen and helium present in the universe? Any answers? The percentage of hydrogen and helium present in the universe? It turns out that hydrogen constitutes roughly 73% of total mass of elements. In the universe. Okay, right? 73%. And helium, approximately 25%. Okay, right? So the rest of it, including the all-powerful and almighty carbon, okay, right? Barely constitute 2%. So it's a very important point to note, okay, right? What are we made of? We, the human beings, we are organic species, right? We are organic species. We are made up predominantly of carbon. But the carbon, that we are composed of is only 2% of the entire universe. Predominantly, most of it is hydrogen and some of it is helium. All right? Please note this point. Okay, so now we have a situation wherein we kind of know how the lightest elements, that is hydrogen, helium, and very little lithium, although we're not concerned particularly about writing the equations leading to the formation of lithium, okay, they were formed right immediately after the Big Bang. So from these elements, that is hydrogen, and how are they all formed? They were all formed by nuclear fusion. See, typically on Earth, when we talk about a chemical reaction, how do chemical reactions happen on Earth? Chemical reactions on Earth, note, and in particular, chemical synthesis, right, on Earth happens through the cleavage of cleavage of a chemical bond and it's only an electron pair that gets broken, and an electron pair is getting broken. I use the word broken very colloquially. Okay, right? However, what happens to the nuclei? What happens to the nuclei? For the major part, the nuclei remain intact unless you're talking about a nuclear fission or fusion that happens in nuclear reactors. Okay, mostly nuclei remain intact. Okay, however, for the formation of the smallest elements, the smallest and lightest elements in space, they required that the nucleus actually be broken. Okay, right? So we're talking about a nuclear reaction that was responsible for the formation of hydrogen, helium, and some lithium back to the beginning. So once this hydrogen and helium were formed, right, these smaller elements can always fuse together in more nuclear reactions to give rise to more and more complicated elements. So we kind of understand I use the phrase kind of because I'm not going to go into the details as to how exactly the other elements were formed. Okay, but we kind of understand that via nuclear fusion, we can form larger elements. And this is nuclear fusion involving the isotopes of hydrogen, helium, and lithium. Along with neutrons, bombardment by neutrons, you have bombardment by electrons, etc., etc. All right. So by nuclear fusion, the larger elements can be formed. We are not discussing them right now, but we shall look into how some of these elements and molecules, some of these elements were formed. Note another point. In our high school chemistry and also introductory college chemistry, we not just talk about atoms. We also constantly discuss about molecules. Correct? Now, how are the molecules formed? How are the molecules formed? Any clue? Any guesses? The point is, see, we are talking about nuclear reactions happening, and when nuclear reactions happen, it takes a lot of energy to break a nucleus and then to fuse it with another nucleus, right? That is some sort of a common knowledge based on high school physics and chemistry. So when that can happen, concomitantly, molecules can also form easily. Nuclear reactions. For example, you take like this 1H1, right? And when this 1H1, which we colloquially represent as hydrogen itself, when this combines with another hydrogen atom, we can always form H2, correct? So when one hydrogen atom combines with another hydrogen atom, right, without the nuclei getting broken, right? So when we were discussing the formation of the higher isotopes, helium, etc., etc., the nucleus was getting broken. But note that without the nucleus getting broken, one hydrogen can combine with another hydrogen to form the H2 molecule also. All right. So when higher energy nuclear reactions can happen, conventional chemical reactions involving the making and breaking of a chemical bond, which is basically a rearrangement of electron pairs, right? That can also happen readily. Okay, right? So this is how molecules can also form in space. Are we fine with this? So we are now in a situation where we kind of understand that molecules can be formed and higher elements can also be formed in space. What with that? How do we proceed further? Now notice that we have this. So we now have a mixture of our current understanding of our understanding based on this lecture, okay, right? Of space. We have some atoms, some molecules, we have some cosmic rays. I haven't told you about this yet, which is basically nothing but is predominantly, largely a stream of proton ray. Okay, right? Which is predominantly nothing but a stream of proton ray, right? So we have cosmic rays, and we also have rays of electrons. Okay, right? So are we clear with this? Okay, right? So space has some atoms, molecules, some cosmic rays, which have some predominantly a stream of proton rays, and we also have some electrons, hanging out here and there. Now, what happens is that these atoms and molecules. So the atoms and molecules which can be bound together by weak chemical forces. When I say atoms and molecules, I'm talking about a bunch of them. Okay, right? Noticing that I'm clearly not defining what a bunch means. I will come back to the question of number and what a bunch means in the subsequent lectures. Currently, please bear with the qualitative description. Okay, right? So atoms and molecules. I deal with a bunch of atoms and molecules without exactly specifying what this bunch is for now. Okay, right? They are bound together by weak chemical forces. Now, what are the weak chemical forces I'm talking about? I'm talking about, the conventional, the van der Waals forces, the dispersion forces, etc., etc. All right. So they all come together and they form what are called as interstellar clouds. Now, the phrase interstellar clouds is something very important, and we shall be using it frequently in this lecture. And what is an interstellar cloud? It is nothing but, a collection of atoms and molecules, right? A collection of atoms and molecules which are loosely bound with each other. And I haven't told you the exact number which is involved in this cloud. For example, what do we understand by the idea of a cloud? We see, especially in hilly regions, right? We see that there are some clouds. The clouds largely comprise of water vapors. Those water vapors are either covalently bound or they are loosely bound. Predominantly, it's water in the gas phase, almost ready to become a liquid phase, right? And there are some metal ions interacting with these water molecules. That's the idea of a cloud, right? The clouds are slightly charged due to the metal ions and some excess charges on the surface of the clouds. Okay, right? So similarly, the interstellar cloud, right, is something that contains a bunch of atoms and molecules. Again, I insist intentionally that I haven't defined what this bunch means. Okay, the number is something very important. I will come back to that in subsequent lectures. So they're all bound together and they form interstellar clouds. Okay, with this understanding, see the inner regions, right? The inner regions of the clouds contains these molecules, right? And when the clouds largely comprises of molecules, clouds predominate with molecules, you typically encounter what is called as a dense molecular cloud. Now it is dense because there are more number of molecules in a volume, in a given volume of space. Okay. However, sometimes, when it is predominantly composed of atoms, you get what are called as diffuse clouds. What is the reason for this? The reason is that typically, when you have like the molecules which are covalently bonded to each other, right? The force of attraction between any two molecules, is larger. So therefore, these molecules occupy a smaller volume. But when there are atoms, the weak chemical forces of attraction between any two atoms is significantly small. And so therefore, right, the net density, that is the number of species present in any given volume, is smaller. So therefore, you get these diffuse clouds. Okay. I also wanted to add one more thing. So along with atoms and molecules, you also have the formation of ions. Well, how are the ions formed? Well, just like molecules are formed, right? If molecules are formed, the formation of ions is also easy, correct? We shall look into the precise formation of ions in a subsequent lecture called as interstellar gas-phase chemistry. Okay. For now, please understand that once the smaller nuclei are formed, the nuclei of the smaller elements are formed. From that, we get the formation of much larger elements. And once the elements are formed, we can form molecules, we can form ions, etc., by a combination of conventional chemical reactions and nuclear reactions. Okay. So once this is established, we know that we have clouds which predominate with molecules. They become dense molecular clouds. How dense, I haven't told you. Okay. Recall that the entire discourse today has been qualitative. I have not given a single number. This is done intentionally because when I compare the properties of space with Earth, I shall be giving you more details about the numbers themselves. Okay, for now, please take this qualitative discussion for granted. So we have dense molecular clouds, and we also have atoms and ions also, which is like going to comprise of diffuse clouds. And typically, at the periphery of these clouds, you can imagine a lot of cosmic rays and the electron rays. They typically do not pass through the clouds itself. It depends on the nature of the cloud. However, you can imagine the periphery, just for the sake of visualization, that at the periphery there's a stronger influence of the cosmic rays, and the core of the molecular cloud are typically protected from the cosmic rays and electron rays. Okay. However, once we understand the formation of the clouds and atoms, we shall now see the important roles played by these rays, okay, right, in the formation of the stars themselves, and how that leads to very interesting astrochemistry. Okay. So in the molecular clouds, both diffuse and dense, okay, right? Now in the molecular clouds, you have, there's always a constant tussle, okay, right? Constant between the kinetic energy of the atoms, molecules, and let's say, the ions with the potential energy due to the gravitational force experienced within the cloud. So, there are also, of course, other kinds of magnetic radiations, etc., etc. But for now, we'll just consider the kinetic energy due to the atoms and molecules by ions. As the molecules and atoms collide within the cloud, the cloud has some kinetic energy. There is also the potential energy due to the net gravitational force, right? Gravitational force within the cloud itself. Now, eventually, an imbalance between the two. I'm not describing what sort of an imbalance. I'm not even writing any equation, but eventually, right? An imbalance, right? An imbalance between the kinetic energy and potential energy results in what is called as turbulence in a molecular cloud. Right? So instead of calling it molecular cloud, one may also, call it like interstellar cloud more generally. Now, what does this turbulence do? This turbulence, okay, right? Eventually, the turbulence causes the collapse of the cloud into a very strong core. A very hot core, dense core. This is the point. So what is the physical picture we're talking about? We have a molecular cloud. We have a molecular cloud or an atomic cloud also. We in general take an interstellar cloud. Now, due to the turbulence between the kinetic energy caused due to the atoms and molecules there, and due to the potential energy due to the gravitational force, some turbulence is produced. This turbulence results in the collapse of the cloud into just the formation of a very dense and hot core. Are we clear? So with this, we stop today's lecture, and in this lecture, we understood that we can have molecular clouds, atomic clouds, and ionic clouds in the interstellar in space, and how due to the turbulence between the different forces, we can actually be seeing a collapse of the cloud into a very hot and dense core. We'll continue further with this understanding in our next lecture. Thank you.